Hello. Why should you look for new physics behind the neutrinos? There are three reasons. First of all, the neutrino interaction probability increases with energy. That allows you to study neutrino interactions better and look for subleading features in these interactions. Second of all, the neutrinos observed by IceCubes travel the longest distance from their sources to the Earth, allowing for small effects to accumulate. Third, these neutrinos come from uncharted territories that will potentially lead us to surprises. So what kind of physics can we look for? We can look for things shown in this cloud bubble with different modes. For example, dark matter can annihilate to neutrinos, they can decay to neutrinos, neutrinos can scatter or interact in vacuum when they come from the source to us, or maybe something happens when neutrino interacts in our detector. All of these will produce different signatures in IceCube. The signatures that we look for actually modify four important observables: the energy distribution of the neutrinos, the flavor of the neutrinos, the number of distribution in the space of the neutrinos, and the time of arrival of these neutrinos. And by looking at this, we can search for new physics. In this talk, because of time, I will only talk about the flavor composition of neutrinos as a prop to search for new physics. So neutrinos are natural interferometers. What do I mean by that? Neutrinos are composed of different mass states. Each mass state is traveling at a different relative speed through space. You can think about neutrinos similarly as a double-slit experiment where light goes along two paths and it produces a light interference pattern. But instead, the neutrino is going to go at two different speeds, and when detected, they're actually going to produce a slightly different pattern, but in flavor. Now, like a normal interferometer, if I put something that modifies one of my lever arms of my interferometers, I will see a change in my screen. In a similar way, if something happens to my neutrinos, I will see a change in the relative flavor observed at Earth. And this is actually extremely powerful because, as we know, in physics, the interferometric measurements are some of the most precise measurements we can do in all of science. Okay, so neutrino oscillations allow you to change the neutrino flavor, and that depends on the neutrino energy and in the difference in masses between each of the neutrino mass states that gives you this phase. And they're actually going to be able to happen in cosmological scales. So when you put in the knowledge that we have about neutrino oscillations in this picture, we can predict the relative amount of neutrino flavors at Earth. Here it's shown in this figure as a flavor triangle, where the horizontal axis is the electron flavor, the right axis is the muon flavor, and the left axis is the tau flavor. What matters here is that the color figures are where you can end up in the standard model, and anything white is not allowed. One of the biggest puzzles in neutrino physics and in physics in general is the nature of neutrino masses. We know that neutrino masses exist, but we didn't know how they come to be. One possibility is that there exist external neutrinos, which are invisible neutrino species. However, the conversion between these our normal neutrinos and external neutrinos requires extremely long baselines as long as the distance from us to NGC 1068. What you can see here in this figure is the probability of converting between our active neutrinos to these stellar neutrino components. So what you see is that you are modifying the spectrum of different sources in the right for a given amount of stellar neutrino mass differences. And the left shows you the significance of possible observation of these stellar neutrinos. And so what we are doing here is we're going to do an interferometric measurements where we have sources of multiple differences that are actually searching for these neutrino flavor transformations. And this has the possibility of unveiling the nature of neutrino masses. Additionally, neutrinos, as they travel through Earth, they sense space, and they're going to be able to probe vacuum, and that's the signatures of quantum gravity. So quantum gravity could produce a Riemann and Lorentz violating fields that permeate space. These Lorentz violating fields can interact with neutrinos as they travel from their sources to us. And what that field does, it introduces a small phase in one of the neutrino states, and that phase difference yields, much like in our original interferometry analogy, it yields a change in the flavor. And so what you see in this figure on the left is different trajectories in flavor space. So IceCube has put constraints in these operators that represent quantum gravity effects, and IceCube constraints are able to reach Planck-scale physics and are the most sensitive probes to this sort of physics. In summary, high-energy astrophysical neutrinos offer unique opportunities for physics. They have the largest energies, traverse the longest paths, and they're able to prove quantum gravity and the nature of neutrino masses. Thank you.